Hello, so let us solve the problem now. We're supposed to calculate the limit of this sequence when n goes to infinity, okay? So if you see what happens for my limit, which is usually you should do this always to understand what type of limit you are facing, by convincing yourself, okay, if I put a very large number here instead of n, this is definitely an extremely large number. That's also the same, then I'm subtracting. So technically speaking, it's an indeterminate form of infinity minus infinity. So in order to solve that, I have to lift this actually indeterminacy. I have to get rid of that. So, and hopefully in the lesson, by solving the examples in the book, you already know what to do with this type of indeterminacy. So you have to multiply or rescale this by the conjugate of this expression, okay? So let us see how it goes. So part A, what I do, I would say that this is the limit. I have square root of n squared plus n plus 1 minus n. Then I rescale it by this conjugate. So what I do, I write this, I multiply this limit, this expression by that. Of course, I'm not allowed to change the problem, so I divide to compensate for that multiplication. So I did nothing actually. I multiplied this expression just by 1, okay? But why this is useful? Because now if I multiply the numerators, this is a conjugate rule, so this becomes the first one squared, which I get rid of this square root, and then minus the second one squared, and then I have this one, of course, multiplied by 1, so this becomes n squared plus n plus 1 plus n, and then n goes to infinity. The good point is that these two are gone, so I will be left with this limit n plus 1 divided by square root of n squared plus n plus 1 plus n, and then goes to infinity. Now what is happening? Okay, if I put n a very big number now, so then the numerator becomes extremely large and the denominator is also extremely large. So now I have infinity over infinity. So what I did so far, I reduced infinity minus infinity, which is one kind of indeterminacy, to another form, which is infinity over infinity. But the point is that we can actually solve that problem. How can I do that? For example, if I ask you what is the highest order, what is the highest degree of what is the degree actually of this with respect to n, you would say 1. Of course, here this is not a polynomial to ask exactly about the degree, but if you want to say a nominal degree of this one, this is of degree 1 definitely. This is of degree 2, but the square rooting it make it somehow degree 1. So the denominator is of degree 1, the numerator is also of degree 1, so none of them will dominate. So in that case, you expect to get a finite number for the value of the limit. You know that if the degree of the numerator is larger, well, then you expect that the numerator will dominate and then you will get infinity. And if the degree of the denominator is greater than the degree of the numerator, eventually the denominator will dominate and then you will get 0. But in this case, they are of the same order, yes? So this means that you expect to get a finite number. Okay, so how do I do that? I divide everything by this n, because n is the highest, is the term with the highest degree. I divide this by n, each term. The first term becomes 1, the second term becomes n. Okay, I divide this by n, that is also 1. Okay, and then if you divide this by n, you can do that. So n squared plus n plus 1, I divide it by n, but instead of n, I can write square root of n squared. But the square root of n squared is really n, because you know that in principle the square root of n squared is not n, is the absolute value of n, always. So I want you to know that when you write square root of x squared, you are not allowed to write x unless x is non-negative. So the general formula that is always correct is to write absolute value of x. So here n is equal to absolute value of n because n is going to positive infinity. And then absolute value of n is equal to square root of n squared. So in this case, n and the square root of n squared are the same. Okay, and then what can I do? I can write it as a square root of n squared plus n plus 1 divided by n squared. Then it means that this becomes n squared over n squared, n over n squared, and 1 over n squared. Okay, so you can do that quickly. So I just write it here. Yes, and n goes to infinity. But in that case, you know that this becomes infinitesimally small, so its limit is 0. The limit of that part and the limit of that part is also 0. So this means that what is left for me is 1 over square root of 1 plus 0 plus 1, which is 1 over 2. So the limit is actually 1 over 2. Okay, now let us go to the second one. In the second one, again, I do the same thing to understand what type of limit I'm facing. So what I do, I put infinity here. This becomes 1 over infinity, which is infinitesimal number. And when I put infinity here, ln of infinity is also extremely large, even though its growth rate is lower than n itself. But anyway, it becomes infinity at the end. 2 over infinity is also 0. So I am facing an infinitesimal value to the power of an infinitesimal value. Technically speaking, this limit is indeterminate of the form 0 to the 0. 0 to the 0 is the name we give to infinitesimal to the power of infinitesimal. Okay, whenever this happens, if you have enough experience, you need to know somehow to use the rules of powers to be able to write that expression, which is expressed as a power with the base 1 over n, write it in the base of the Euler number e. So let me just remind you a little bit here. So assume that I have a power, I have a b which is positive. This b is positive, and then b to the power of x, it's an exponential function whose base is b. I can always write it as an exponential function whose base is e. How? I can write it in this form. I can write e to the power of x ln of b. I want you to know that these two are the same if b is positive. Where is it coming from? This is actually the definition of the natural logarithm. So you know that e, which is the base of the natural logarithm, to the power of ln of a positive number, say a, this is always equal to a by the definition of the natural logarithm. Yes? Okay, now what we do, I interchange this a in the definition by a b to power x. Okay, so then how this will read, this becomes ln of, instead of a, I put b to the x, and instead of a, again, I put b to the x. But we know one property of the natural logarithm, that this x can go behind, so this becomes e to the power of x ln of b is equal to b to the power of x, or any other way that you can convince yourself it is true. So this means that this means that in a simple language, it means that if I have an exponential function with the base b, which is positive, I can write it as an exponential function whose base is the Euler number e. Okay, and whenever you are facing these kinds of limits or other types, for example, 1 to the infinity, infinity to the 0, this is always good to think about this trick that I'm going to use to solve this limit. Okay, so what we do, I want to use the same idea. So I would say that this limit that let me write this in front of our eyes. This is my limit. So what I do, I will write this expression, which is a power in base 1 over n, as a power in base e. Okay, so what can I do? I can say that this is the limit. Okay, so here, if you compare this with that formula, look here. I want to give the role of 1 over n to b, and I want to give the role of 2 over ln of n to x, and then write this expression. So this becomes limit e, and then instead of x, I put 2 over ln of n multiplied by ln of b, but this is my b in this problem. So this becomes ln of b. N goes to infinity. Okay? So in order to calculate this limit, I can, instead of calculating this limit, I can calculate this limit. But there's also another theorem that if you want to calculate the limit, so let me just write it here. We can also, of course, talk a little bit about that. If I have e to power a sequence, e to power an, and if I want to send n to infinity, I can do this if, of course, the limit exists. Yes. So this we can do if an is a sequence whose limit an exists, then the limit of e to the power of that sequence, of course this is a new sequence, if you want to calculate the limit of this new sequence, it is allowed to write e to the power of the limit of that sequence. I will actually mention the theorem that justifies this, but for the time being, take it for granted. Let us continue and solve the problem. So this means that in order to answer the question, I need to write e, and then of course I have to first convince myself the limit of this part exists. So let us convince ourselves about that. So we stop here, we come here and try to see if that limit exists. This is limit ln of n. We want to see if this limit exists because I want to use this theorem. One assumption that this theorem lies on it is that the limit of this exponent exists itself in the first place. Okay, so I calculate this limit. Is it possible to calculate this limit? Extremely simple, yes, because you know this famous formula in ln. So this becomes ln of a, of course if a and b are positive values, minus ln of b. But now let me choose a to be 1. Then this becomes ln of 1 over b is equal to ln of 1 minus ln of b, but you know that ln of 1 is 0, so this means that ln of 1 over b is nothing except ln of b. So ln of the reciprocal of b is the opposite of ln of b. So here, what can I do? I can copy and paste this part, and then instead of ln of 1 over n, I can write minus ln of n. But then, and n goes to infinity. But then you know that this limit, this ln and this ln are cancelled, so this becomes the limit of minus 2 when n goes to infinity. But minus 2 can be viewed as the constant sequence, so its limit exists and it is equal to the value of the terms of the sequence. So the limit here is 0. So it is guaranteed that the limit of this exponent exists and is equal to minus 2. Now I can use this theorem and safely write e and move the limit to the exponent part. So the limit of 2 over ln of n, ln of 1 over n, n goes to infinity. But I have already calculated this part for you. We got minus 2, so the answer becomes e to the power of minus 2. And then, of course, you can write it as 1 over e to the power of 2 as well. So this is the final answer to this limit. Okay, so this theorem is more generic than that. Okay, so e, exponential function, is among one of those functions. The main property that makes this possible is continuity of the exponential function. So if I want to refer you to the problem, to the theorem, is this. So assume that you have a sequence an, and you know that the limit of this particular sequence exists, and say it is equal to the real number L. This is a sequence in the real numbers. And on the other hand, you assume that you have a function, for example, accepting real values, giving you back real values. You have that function, but with a property. This function, whatever it is continuous at the point L. L is a number, say 5, and this is a function which is continuous at 5. for example. Okay, and then from this function and from this sequence, I can make a new sequence. For example, I would say that let Bn be f of an. I hope that you agree. So an is a list of numbers. I take them one by one and feed them into this function. I get real numbers back. When I put a1, it gives me a number, I call it b1. When I put a2 here, it gives me a number, I call it b2. Then I have b1, b2, etc., which is a new sequence. Okay? Now my question is that, what can I say about the limit of this new sequence that I generated that way? I would say that, okay, if the limit of the original sequence exists and the answer is L, and if, this is the big if, and if your function is continuous at that point, then if you want to calculate the limit of b of n, when n goes to infinity, the answer is so simple. The answer is f of L. L is that number. In other words, if I want to write it in a more nicer way, instead of bn, let me write f of an. Okay, n goes to infinity. And then fl, so let me write f, but instead of l, let me write that. It becomes limit of n goes to infinity. It's a very nice relation, but this is not always true. So you see, it seems that I am slipping this limit sign into the function. Yes? But this is only valid if two conditions. This limit exists and the function is continuous at this limit. So what I did here, that you see, is just a very special case of this one, in which the function f of x is chosen to be the exponential function. Okay? If f of x is e to power x, let me repeat this. Then this becomes the limit. Instead of f of an, I can write e to power n to infinity is equal to f, which is the exponential function, e to the power of this limit. So that's exactly what I wrote here. So this is one particular case. Why it was valid, by the way, here? Because the exponential function is everywhere continuous. So it means that if the limit of this exists, it is already guaranteed that the exponential function is continuous at that point, because the exponential function is continuous everywhere. Okay, so this is also good to know. So this is more generic than that. So if I have a function of a sequence and I have a limit of that, I ask myself, can I move this limit inside? So in other words, if I take f and take the limit, would it be the same if I take the limit first and then apply f? The answer to this is always yes, under two important conditions. First of all, the limit of your sequence should exist, and secondly, the function should also be continuous at the value of that limit. Okay, so I hope that this video was useful for you. Until the next video, be safe and goodbye. Thank you.